In example 3, we're looking at heights of adult women in the U.S. Jose finds out that women are 65 inches tall on average, at least that's what it says on the internet, and have a standard deviation of 3.5 inches. He wants to test whether that's accurate. So he collects a random sample of 123 adult women, and the women in his sample have an average height of 64.3 inches. All right, so the research question for Jose's study is the average height. This is of all U.S. women. This is about the whole population. 65 inches, right? So the population that he's trying to understand something about is all U.S. women, not just the 123 women in his sample, but all adult women in the U.S. All right, Part B asks, what shape would the population distribution probably have? If you've already watched the video for example 4, I mentioned heights there. Heights tend to be normally distributed, right, where most people are kind of in the middle in terms of height, and then you have, a decreasing number of people that are shorter and a decreasing number of people that are taller than that. And the taller and shorter you go, the fewer people you have at that height. All right, is Jose's data categorical or quantitative? So again, it's best for us to realize what the observational units are, U.S. adult women, and what piece of data did Jose collect from each of those women. That's our variable, which is height in inches. And notice, it's not average height, it's just the woman's height in inches, and this is quantitative. So even though it didn't directly ask about the observational units in the variable, it's kind of necessary to figure those out to know what kind of variable we have. So this is not categorical, it's something that we can measure and that has units. Now, since our variable is quantitative, the symbol for the parameter is going to be mu, and mu is always an average, and it's an average for the whole population. So this would be the average height, and that, of course, is in inches, of all U.S. adult women. And as is generally true of parameters, we do not know the value. The value is unknown. We are going to make an assumption about the value of the parameter to create our null hypothesis and be able to do our analysis. But generally speaking, the value of the parameter is not known. All right, so the null hypothesis, we're going to start by assuming that what Jose read online is true. So notice that this is not really about random chance in the way that it was with categorical variables. Our null hypothesis is, all right, let's assume that what he read online is true. If that's the truth, then what are the chances of seeing a sample like the one Jose got? Now, in order to figure out, so we know that our alternative hypothesis is going to have a mu and it's going to have a 65. And now we have to figure out what symbol goes in between those two. Is it less than, is it greater than, or is it not equal to? Now it says in the scenario, the statement of the example, Jose wants to test the accuracy of that online fact. So in other words, he's not supposing or conjecturing that the average height is less or more than that. He just wonders if that's accurate, which means we have a not equal two-sided alternative hypothesis. Now, in words, we would say the average height in inches of all U.S. adult women is 65 inches for the null hypothesis. And for the alternative, the average height in inches of all U.S. adult women is not 65. So I would substitute for mu the entire sentence that's in part D. and then is 65 for the null and is not 65 for the alternative. I'm just going to save a little time by not writing them out. Now we're going to do a simulation with the one mean applet. We're going to create 1,000 samples. So let's go to the applet and see how that's done. So we're in the one mean applet, and we are going to create a population model. And according to what Jose read online, we're going to assume that's true. The population mean is 65, and the population standard deviation is 3.5. So we're going to make those assumptions, and we're going to keep the shape at normal. And you can click Set Population if the graph doesn't change automatically. So we see this bell-shaped distribution, which again is typically how heights are distributed. Most people are kind of in the middle, and then you have a few taller and a few shorter. Now we are going to take 1,000 samples of size 123, which is the sample size that Jose used, and whoops, I clicked it twice by mistake. That's okay. So I actually have 2,000, but you can just do it with 1,000 samples. So again, here we have 3 different distributions. On the left-hand side is the population distribution. Those, all you see is that blue curve, but you can imagine millions and millions of dots underneath that. And along the horizontal are heights of individual U.S. adult women. In the middle, we have a sample distribution, and right now it's the most recent sample, but if I click anywhere in the gray graph on the right, I can see individual samples, right? So here's sample, well, that's sample 1101. Here's sample 155. So we have a sample distribution, so there are 123 dots in that middle picture that got pulled out of the hypothetical population on the left at random and put into this distribution. So this sample has a mean of 64.5 and a standard deviation of 3.6, which are similar to the population mean and population standard deviation. And any individual sample that you look at will have roughly a bell shape, a mean close to 65, and a standard deviation close to 3.5. And then on the right-hand side, we have a null distribution. Notice the label on the horizontal axis is sample means. The word means is really important. So along the horizontal, those numbers are averages from groups of 123 women. So notice how on the left graph and the middle graph, the numbers on the horizontal axis go from 56 to 77. That's how much individual women's heights might vary. But the graph on the right, the null distribution, only goes from 63.7 up to 66, which means the averages from groups of 123 women don't vary nearly as much. So notice that the mean of this null distribution is 65, which is, it's 65.003, but basically the same mean as the population. But the standard deviation is only 0.325. That's much lower than the standard deviation in the population, that's 3.5, or the standard deviation of any individual sample. And again, if you click around and just notice the sample standard deviations, they're all close to 3.5. All right, so if we want to find a p-value, generally speaking, we put our statistic into the count box, and well, I got to go back and look it up. The mean from Jose's sample was 64.3 inches. So that's what I'm going to put in my count box, 64.3. So in general, what goes into the count box is the sample statistic. In this case, it's an X-bar value. Now, once again, my entire graph is red. That usually means that something is wrong, and it's probably this drop-down box. So let's think back to our alternative hypothesis that had a not equal to in it. So I'm not looking for greater than or equal. I'm not looking for less than or equal. I'm looking for beyond. So this is a little different than the one proportion applet that had a little box you would check for two-sided. In this applet, we can just choose beyond from this drop-down in the count box area, and that will automatically do a two-sided test. So here I have 57 out of 2,000. So I kind of want to cut that in half, but I'll just go with it. But yours might only be out of 1,000, and that's good. You should do this for yourself. But my p-value is 0.0285. So let's go back to the worksheet. So the p-value for this study, for me, again, because I accidentally took 2,000 samples, was 57 out of 2,000, but it also gave me the decimal for that, 0.0285. So interpret the p-value. This again is a probability of what, assuming what. There is a 57 out of 2,000, or you could write the decimal, 0.0285 chance of getting a sample mean at least as extreme as the 64.3, and actually, let me put the symbol with that as well. And I'm going to write in parentheses in both directions, meaning we're doing a two-sided test. Assuming the null hypothesis is true, but I don't want to write it that way. I want to write it in context, assuming the average height of all U.S. women, the whole population, is actually 65 inches. So that's the interpretation of the p-value. And remember, there's that file, Chapter 1 Interpretation Examples file in Blackboard that you can look at to remind you of how we do these interpretations. And then we're supposed to evaluate the strength of evidence against the null hypothesis. With a p-value between 0.01 and 0.05, we have strong evidence against the null hypothesis. All right, so in conclusion, the conclusion usually is about the alternative hypothesis. What conclusion should Jose make about women's heights? There is strong evidence for the alternative, but again, I need to write that in context. There is strong evidence that the average height of all U.S. women, adult women, I guess woman implies adult, is not 65 inches. That was what we stated in the alternative. So if we have strong evidence against H0, that means we have strong evidence that the research conjecture HA is the truth. We can't say it definitely, but we have strong evidence for that. All right, now suppose Jose's sample actually had 1,230 women, and his sampled women had an average height of 64.3 inches tall. Rerun the simulation with this new information. Okay, so let's go back to the simulation, to the applet. Whoops. And we're going to put in a sample size of 1,230. And we're going to draw 1,000 samples. Now, here's a couple interesting things to note. First of all, if I click around in the gray graph but pay attention to the middle picture, these different sample distributions, notice that each one is sort of more bell-shaped than in the previous example when we had sample of size 123. So when we have a larger sample, it's sort of, in a sense, in quotes, more representative of the population. So its shape is closer to normal with a longer run of trials in our sample. Now, just like before, if you click through these a little more slowly, each time you get a bell-shaped distribution, so it looks like the population, and you get a mean that's close to 65, and you get a standard deviation that's close to 3.5. So in the middle is a sample distribution. The left-hand side is still the population distribution, which has not changed. Now, my null distribution on the right, notice my standard deviation has gone down some more. It's now only 0.102. Before it was more like 0.3. It was 0.325 before. So increasing the sample size has decreased the variability, not of the sample, that's still 3.5, not of the population, that's still 3.5, but it's decreased the variability of the null distribution, which has gone down from 0.325 to 0.102. And now, when I look for 64.3, which was in the tail of the last null distribution, but here it's not even in the picture. So if I put the 64.3 back in the count box, and it has saved my beyond two-sided alternative value there, notice now I have 0 out of 1,000 of my sample means came out at least as extreme as 64.3. And it's counting in both tails, even though you can't see anything because there's nothing red there. Okay, now Jose has very strong evidence that the average height of all U.S. adult women is not 65 inches. So our p-value was 0 out of 1,000. So we've gone from strong to very strong. So the evidence against the null hypothesis has gotten stronger. So part J, describe what happened to the p-value as Jose increased the sample size from 123 to 1,230. P-value decreased. It went from 0.0285 to 0 out of 1,000. And then describe what happened to the strength of evidence against the null hypothesis. Strength of evidence increased, got stronger, from strong to very strong. And so it says, why did this happen? This is because the variability standard deviation of the null distribution, not the standard deviation of a sample, not the standard deviation of the population, but of the null distribution, decreased from 0.325 to 0.1. Was it exactly 0.1? I'm anally retentive. I've got to go check. 0.102. Doesn't really matter. I just had to do that. The variability, the standard deviation, the null distribution decreased from 0.325 to 0.102. So the sample statistic which was x bar equal to 64.3, is further in the tail of the second null distribution. With the larger sample size. So we increased the sample size. This decreased the variability in the null distribution. So the same sample statistic of 64.3, it was in the tail originally, then it moved further into the tail when we increased the sample size, decreased the standard deviation of the null distribution. Now, another little thing before we go, you could check S over the square root of n. When n is 123, well, actually it's not S. I should take that away. Well, I'll just write standard deviation. The population standard deviation was 3.5 over the square root of the sample size 123 versus when n was 1230. If we were to take 3.5 over the square root of 1230. Now I haven't done the math on this, but this one's going to be about 0.325 and this one's going to be about 0.102. And I'm just going to take a brief moment and put this into the calculator on my cell phone, and you should pause this video and try it yourself. So 3.5 divided by 123 square root up 0.316. That's what I got doing the actual calculation. If I take 3.5 divided by 1230 square root, I get 0.100, which is pretty close to 0.102. So just pointing out to you, if we knew the standard deviation in the population, so let me just make a note, this is the population standard deviation, and divided that by the square root of the sample size, we get approximately the standard deviation of the null distribution.